I want to remind you guys again that I believe the homework 2 has been posted to EE class, okay? So if you have not downloaded it, I mean, please check it out, okay? The due date is like next Friday, so you have about 10 days to work on that. I just hope that you guys will have a good spring break. So I set the deadline prior to the spring break. Okay, so that's it about the other stuff. So I'll come back to the material that we covered last time. Okay, remember we used we talked about a strange chemical shift stuff. Remember, and we try to model this by a normal or Gaussian distribution. Okay, which has two parameters. One is the average, mu, okay, mean. The other one is the standard deviation, sigma, okay? And mean, we model it from a uniform distribution, and for sigma, we model it from a half normal, okay, because sigma is always positive, okay? So, and then we use the pi MC3 to generate the result. Because it has two parameters, so we have two of these. And the reality is that it's going to look like a three-dimensional, so we are able to see the joint distribution, something like this. Okay, I mean the top-down view, okay? So we talked about this last time, but yeah, this is the summary of the posterior for the mu and the sigma, okay? Of course, these represent the marginal probability distribution summary, because the whole thing is a joint probability anyway, okay? So, but is this model good enough? Okay. We learn how to critique the result at the end of last chapter, okay? If you still remember, we call that posterior predictive check, okay? And we only talked about the concept, okay? But we really didn't offer example at that time because, to really do posterior predictive checks, we need program, we need computer to help, okay? But now, okay, in this chapter, since we now know pi MC3, so we are able to do this posterior predictive check. If you still remember, okay, what we are doing is that we sample the parameter from the posterior, and then we use those sampled parameter, in our model, okay, and because we have a likelihood, remember? So from the likelihood, we are able to generate data, okay? It looks like a prediction, okay? It looks like a prediction. So the whole thing is called, that's why the whole thing is called the posterior predictive check, okay? Because we want to see if the data generated from the posterior along with the model, okay, how well the data match our original data, Okay, so yeah, so we're using posterior to make predictions. So we are using these predictions to check the model. So well, so now, okay, with the help of the PyMC3, okay, we are able to do that. Okay, so first thing first, okay, we need to generate the samples from the posterior, right? So here is the thing, okay. So well, actually, PyMC3 is they already built a posterior predictive check, function, okay, for us. That's this one. Sample posterior predictive, and in this function, okay, remember the process of the posterior predictive check. You need two things, okay, to really generate the data. The first thing is the trace. This trace represents the posterior, right? The trace contains the posterior of the parameter, right? And then you can sample from this posterior. After that, you put this sampled parameters to the model, because model contains the likelihood, right? And then you have a likelihood, you are able to sample again from the likelihood. Okay, so here, okay, you put this trace G, which represent the posterior, and also you provide the model G. Okay, this one tells like this function, like what is the likelihood, okay, that it can use to generate the prediction, okay, that 100 just means like you want 100 like predictions, okay. So after you have that, okay, you store this result here, y pred, okay, g, okay. This y pred g is a dictionary, okay. Why is it a dictionary? Okay, because for a model, okay, we could have more than one observed variable. I mean, so far, like the examples that we have, okay, we have only one value. For example, like coin flips, okay, it's either like head or tail, or like this shift stuff, like the y that we are talking about, okay, is this thing, right? These values, okay. So yeah, I mean, for the existing the examples that we have talked about, okay, I mean, the model, okay, is built for like just like single value, okay. Even though sometimes model may have one parameter or more than one parameter. For example, like in a coin flip, like we only have one parameter, which is the theta. Okay, for this gamma, normal distribution. Okay, we have two parameters, mu and the sigma. Okay, but the eventual data. Okay, for data, okay, we always have like just one single value, but this is not always true. Okay, sometimes for some experiments, we may have like more than one data. For example, okay, say like if you want to collect like the location data. A location data comes with two dimensions, right? I mean, suppose we are collecting two-dimensional location, right? So it comes with two dimensions. And there are other, vast examples, where the data may be multidimensional, okay? So that is why, okay, in this posterior predictive check, okay, the function, okay, generate this dictionary, okay, type of variable, which, is able to accommodate, okay, like, if the problem you are dealing with, okay, happen to be multidimensional, okay. So, okay, then we can use the plot PPC function, okay, for visual posterior predictive check. So here, okay, is the code, okay, that we plot this next figure, okay. So if you still remember, okay, the dark line, okay, represent the observed y, the kernel function, function of the observed y. You can consider that as like a smooth, histogram, okay, a smooth histogram of this thing. Remember, just this thing. Okay. But you may ask, what are those wonky, like a blue, like hairy lines behind? Okay, basically, okay. Remember, we are generating 100 samples. Okay, so each sample we try to draw a kernel function, just like what we did for the real data set. Okay, and so because we generate like 100 samples, right? So each one will be represented by well, is it blue, right? Blue line, okay. You should be able to observe. So we have many blue lines, okay. And you first, of course, you check the consistency between the real data and the generated one, and see like if they match in certain aspect, okay. How do you think, by the way? Do you think it's good enough? Any comment? No comment? Okay. First thing first, if you really look at this, a little bit closely, you would have found that, okay, the center, okay, probably I shouldn't use center, I should use mode. The mode, okay, of the real data is here, right? Okay, the highest point is here. But if you look at the samples, the lines that generated by the samples, it seems that the average or mode move a little bit to the right, right? It doesn't match so well, okay? It doesn't match so well, okay? So, is it is it good enough? Okay. Of course, okay, to really have a final saying whether or not this is represented, the result of the model is representative, okay, again, it requires certain background knowledge at this particular research domain, which is like quantum chemistry stuff, okay. I don't know about that, okay, but remember I told you, okay, the author is an expert in that, research field. He has been working on that, for a long time, okay. So basically, okay, yeah, so this KD is drawn by the obvious, okay. So, yeah, I already explained this, but okay, from the figure we can see the mean of the simulated data is slightly displaced to the right. This is, I hope this is obvious. It's not, if it's not, you probably want to use the computer to generate it because, when we print it on the paper, it's not as clear as it is to the computer screen. But one thing is that, okay, you may wonder, like, why don't we draw those 100 lines darker, okay, more thicker, okay. It is, it is because, like, it's the author claimed this is a feature of RVs, okay. Some people will think this is a bug, okay. But the author thinks this is a feature, okay, because it reflects the property that of the data instead of almost over smoothing it. Basically, like, this data, the predictions